Hello everyone, my name is Nivas. I'm a student of Institute of Aeronautical Engineering, UNITARY. So I'm a computer science engineering student of B section. Today the tech talk PPT subject is linear algebra and calculus, which is shortly known as LAC, and the tech talk topic is unitary matrix pencils in signal processing. Abstract. The problem of retrieving harmonics of a measured signal can be solved via solving an eigenvalue problem for a unitary Hessenberg matrix H built from the first square parameters of the Toeplitz matrix of the signal autocorrelation coefficients. From the eigenvalues E for theta k, we get the approximated frequencies theta k, and from the first components of the corresponding eigenvectors, we get amplitudes. The eigenvalue problem for H is equivalent to eigenvalue problem for the unitary matrix pencil G0 minus lambda GE, called the square parameter pencil. The eigenvalues being the same for both problems. The advantage of working with this generalized eigenvalue problem is instead of solving the standard eigenvalue problem for H lines, in the sparsity of matrix pencil G0 minus lambda GE, the only non-zero entries being in the fact of square parameters. Solving the retrieval harmonics problems as a unitary eigenvalue problem also has the advantage that we can make use of mathematically rich eigenvalue structure of unitary matrices, which by this allows in particular to give bounds on the distance of the computed approximations to the frequencies to the actual frequencies. We present such results and numerical examples showing the accuracy of the method and effectiveness of the perturbation results. What is matrix pencil method? The matrix pencil method MP is a direct data domain method that can be used to estimate direction of arrivals, which is DOA, of correlation and uncorrected signals. Although most popular methods are based on estimation of the signal correlation, which requires several snapshots of the incoming signals. So, coming to a pencil, what is a pencil? A pencil is called regular if n is equals to m and det of a plus xb, which is determinant of a plus xb, does not vanish identically. That is, if there is lambda is belongs to C, for which it is a square invertible matrix. So here we can see that in the screenshot. This is the example of a pencil, the equation of the pencil, where here x is an intermediate value. So coming to what is an eigenvalue? An eigenvalue, lambda, it is denoted by lambda, is a value for which determinant of a plus lambda b is equals to 0, eigenvector and Jordan chains. If determinant of a plus xb has degree less than n, the missing eigenvalues are said to be at infinity. So this is the example of finding an eigenvalue of a matrix. So this is how a matrix pencil method works, and these are the factors depend upon matrix pencil method. Eigenvalues of singular pencils. Eigenvalues of singular pencils can be defined via unusual rank drop. For instance, this is A plus xb form. This is the matrix of A plus xb, which has typical rank 2. Here we can see that this matrix has rank 2. More formally, if rank C of x into A plus xb is equals to 2, but in place of x, if we place to number 2, then we'll get rank 1, which is called as unusual rank drop. From 2 to 1, it is known as unusual rank drop. What is a canonical form? In mathematics and computer science, a canonical form or normal form or standard form of a mathematical object is a standard way of representing the object as mathematical expression. The row echelon form is a canonical form when one considers as equivalent a matrix and its left product by an invertible matrix. This is a simple example of a canonical form matrix. For a regular matrix pencil A plus xb belongs to C, there are non-singular P comma Q belongs to C again, such that P of A plus XB into Q is directly sum of blocks of the forms. Means P of A plus XB of Q is equal to sum of the blocks of the forms. Here we can see that J lambda of X, J into J of X are forms, blocks of forms. So coming to this slide, what is a Heisenberg matrix? In linear algebra, a Heisenberg matrix is a special kind of square matrix, one that is almost triangular. To be exact, an upper Heisenberg matrix has 0 entries below the first subdiagonal, and a lower Heisenberg matrix has 0 entries above the first superdiagonal. They are named after the great mathematician Carl Heisenberg. So Carl Heisenberg is one of the mathematician, and Heisenberg matrix has got name after Carl Heisenberg scientist. So this is a basic example of square matrix, and we can visualize it. And this is a triangular matrix where if the elements in the second row first column are 0, and second row first column and second row first element and second row second element are zeros in this triangular form, then it is called as a triangular matrix. Any triangle in the matrix which are zeros is called as triangular matrix. Let's go to the next slide. Upper Heisenberg matrix. A square n into n matrix A is said to be an upper Heisenberg form of to be an upper Heisenberg matrix if Aij is equals to 0 for all I comma j with I greater than j plus 1 times is greater than I. An upper Heisenberg matrix is called unreduced if all subdiagonal entries are non-zero. If all these subdiagonal entries are non-zero, that is, if Ai plus 1 comma identity matrix is not equal to 0. The identity matrix and Ai plus 1 value, if all they are not equal to 0, then for all belongs to 1 to so on n minus 1. So this is the basic example of upper Heisenberg matrix. So as we have discussed previously, that this triangle which contains zeros is known as upper Heisenberg matrix. So this is an upper Heisenberg matrix. Coming to the lower Heisenberg matrix, a lower Heisenberg matrix is called unreduced if all superdiagonal entries are non-zero. That is, if Ai plus 1 comma identity matrix is not equal to 0 for all I belong to 1 to n minus 1. This is similar to upper Heisenberg matrix, where lower Heisenberg matrix forms 0 in this place, which Heisenberg matrix is nothing but a triangular matrix, as we can have discussed in the earlier slides. So this is how a lower Heisenberg matrix looks like. This is one of the example of it. Signal processing. How is linear algebra used in signal processing? It has many useful applications in signal processing, and statistics include which computing the pseudo inverse, least square fitting of data, multivariable control, matrix approximation, and determining the rank, range, and null space of the matrix. This is one of the process of signal processing used in unitary matrix or any other type of matrix to find them. Linear algebra and making it optimized in the probability and statistics, and deep learning about the content, deep learning about the matrix. So probability and statistics and optimization from the linear algebra, and deep learning the particular matrix. Stable matrix. An n into n matrix A with real entries is said to be a Schur stable matrix if all the eigenvalues of A are inside the open unit disk. We investigate the structure of linear maps on the Schur stable matrix that preserve the collection of S of Schur stable matrices. This is how the values are inside the open unit disk. So these x, y, and x are inside the open unit disk. So this is how a stable matrix looks like. Correlation matrix. Cross correlation is generally used when measuring information between two different time series. The possible range for the correlation coefficient of the time series data is minus 1.0 to plus 1.0, negative 1 to positive 1. The closer the cross correlation value is to 1, the more closely the sets are identical. If the value of cross correlation is more closer to more relevant to 1, then the sets are said to be more identical. So this is how a cross correlation matrix looks like. This is an example. Rx have the two elements here. So this is how the cross correlation matrix looks like. Let's move on to the next slide. Eigenmatrix. The roots of the characteristics equation is called eigenmatrix or characteristic roots or latent roots or eigenvalues. Eigenvalues and eigenvectors. Here we find eigenvectors by their eigenvalues. So if you have a matrix like 4, 1, 3, 0, 2, 1, 0, 0, 3, then we have to subtract with the eigenvalues in this matrix. Only the diagonal elements are subtracted with the eigenvalues so that you get to find eigenvectors. So this is the result of the matrix. So we multiply this matrix, the obtained matrix, with x is equal to 0. Solving that, we get equations. The first row can form an equation, second row can form another equation, and third row can form another equation, which are first, second, and third equations respectively. If x3 is 0 and x2 is also 0, then we can consider x1 as k, so that if we consider one element as k, so then we can find all other eigenvector values by substituting those values in the equations. So this is the obtained eigenvector value, which is k, 0 and 0. This is how we find eigenvalues and eigenvectors with eigenmatrix. What is unitary matrix? A square matrix said to be a unitary matrix when A into A power theta is equals to identity matrix, or A power theta into A is equals to identity matrix, which is neither the same. Here I is a unitary matrix, is an identity matrix, as we all know that I is an identity matrix which 1 0 0 0 1 0 and 0 0 1 in 3 by 3. So this is the example of a unitary matrix. This is how it looks like. Let's go to the next slide. Diagonalization of a matrix. A square matrix A is said to be diagonalized if there exists a non-singular matrix P such that P inverse AP is equals to D, where P inverse AP is equals to D, where D is the diagonal matrix. Finding the diagonalization of a matrix is just converting a matrix into a characteristic equation, which is A minus mod of A minus $I. Here, why I am taking dollar means it could be lambda, it could be any other character, but for an instance, I am taking dollar here, so that to understand very easily, A minus $I or A minus lambda I form, and the following procedure continues with the determinant of the matrix and then finally finding the eigenvalues of the matrix. So we are using P inverse AP formula or diagonalization formula on a particular matrix problem. So this is the procedure to do a diagonalization of a matrix so that we get the diagonal matrix as 3 0 0 1. So this is the example of diagonalization of matrix, and this is how we use diagonalization of matrix. Let's go to the next slide. What is a matrix approximation? The unstructured problem with fit measured by the Frobenius norm, that is, has analytic solution in terms of singular value decomposition of the data matrix. The result is referred to as the matrix approximation, lemma, or Eckart-Young-Mursky theorem. So there are two theorems for the matrix approximation, which are lemma or Eckart-Young-Mursky theorem, and Frobenius according to the Frobenius norm. So this is the example of this is how we do the matrix approximation. So let's go to the next slide. So Cayley-Hamilton theorem. In linear algebra, the Cayley-Hamilton theorem, named after the mathematicians Arthur Cayley and William Rowan Hamilton. These are the two mathematicians who found, because of them, Cayley-Hamilton theorem was named, which states that every square matrix or a commutative ring, such as the real or complex field, satisfies its own square matrix. Means a square matrix satisfies its own characteristic equation. Means here characteristic equations means A minus lambda I is equal to 0, or A minus $I, as we have discussed earlier, is equal to 0, which has to be mentioned in modulus. An application of the Cayley-Hamilton theorem to generalized matrix inversion. Introduction. The Cayley-Hamilton theorem is utilized in finding the generalized inverse of an arbitrary complex matrix. The main result gives rise to an algorithm to computing the generalized inverse. Preliminaries of this application. The concept of matrix inversion has been generalized independently by Penrose. Penrose is a mathematician. The Penrose formulation states that for any matrix B, the four equations which are B x B is equals to B, x B x is equals to x, Bx is equals to Bx, and xB is equals to xB. These all have a unique solution of x denoted by x is equals to B inverse and called as the generalized inverse of B. Price has given a resume of some basic properties generalized inverse. So we'll discuss fundamentals and theorems and proofs in this slide. So according to theorem 1, a necessary and sufficient condition for the matrix equation Pxq is equals to C to have a solution is P inverse, C Q inverse, and Q is equal to C, in which case the general solution is this equation, as we can see here. X is equal to P inverse CQ inverse plus Y. Here Y is an arbitrary to within having the dimensions of X. Y is an arbitrary having dimensions of X minus P inverse into Py into Q inverse. This is how the theorem 1 states. Coming to theorem 2, according to Cayley-Hamilton theorem, let f of lambda is equals to minus 1 whole power n of lambda power n plus a1 lambda power n minus 1 plus so on up to a n minus 1 lambda plus a n, which is the characteristic polynomial of n into n unit and 0 matrix B. And let I and Z are respectively denote the n into n unit and 0 matrices, where here we can see that I denotes n into n unit matrix, unitary matrix, and Z denotes the 0 matrices, which we can see in this equation b power n plus a1 b power n minus 1 plus so on up to a n minus 1 b plus a n I. n I means n into n unitary matrix is equal to Z is a 0 matrices, which is 0 0 0 0 0. Main result of theorem 2. Let A be any n into m complex matrix, and let this equation with a naught is equal to 1, having the value a naught is equals to 1. If a naught is equal to 0, then the first element, this first part, the whole thing becomes 0. Second part will also become 0. So that is the reason we have mentioned that a naught has to be 0. It has to be 1. So this be the characteristic polynomial of a into a inverse. If k is equal to 0 is the largest integer, such that AK is equals to 0, then the generalized inverse of A is given by this equation. A inverse is equals to minus AK whole power minus 1 A into A whole power k minus 1 plus A1 into A into A whole power k minus 2 up to A k minus 1 into I, which is a unitary matrix I. If here k is equals to 0 is the largest integer such that AK is equals to 0, then A inverse is equal to 0. If AK is equal to 0, then A inverse is also 0. Because as we have discussed that A naught has to be 1, then only A naught will get a certain output. Or else if we keep A naught is equals to 0, the whole equation becomes 0. So that is the reason here the statement says that AK is equals to 0, then A for A inverse is equals to 0. If AK is 1, then A inverse will be some value. Proof. According to the Cayley-Hamilton theorem, A into A inverse satisfies its characteristic equation, that is this equation. A into A whole power n plus A1 into A into A whole power n minus 1 plus so on up to A n minus 1 A into A plus A n I is equals to Z. Conclusion about signal processing from pencils. A unitary transform for the two-dimensional matrix pencil method has been successfully formulated and utilized to convert the complex data matrix to a real matrix. This is how this graph shows that the conversion of complex data matrix into real and simple matrix. This is how the graph represents. Hence, reducing the computational complexity. This is how the graph reduces here to reduce the complexity and computational complexity significantly in DOA estimation problem. If it is seen that the lower SNR of the data 2D matrix polynomial performs the better than 2D UMP matrix pencil performs better than 2D unitary matrix pencil. After a certain threshold, both the matrix pencil and the new unitary matrix pencil method can be used to model a given data set by a sum of complex exponentials, and the unitary matrix pencil can be implemented on a DSP chip using only a real arithmetic. Here, DSP chip is the type of technology used in signal processing. So DSP chip is used for that using only real arithmetic. So this is the conclusion of matrix signal processing and matrix pencil. Thank you everyone. Activity is finished.